Welcome to another lecture of the course Mathematical Aspects of Biomedical Electronic System Design. Today's lecture will be the last one on linear algebra. In this lecture, we will look at system of linear equations, Cramer's rule, Gaussian elimination, something called row echelon form of matrices. We will also see various uses of Gaussian elimination. So let us begin today's lecture. We will start with system of linear equations. Systems of linear equations. Okay. So to begin with, let us fix numbers a1 to an, these are real numbers, and another one b, and also consider variables x1 to xn, these are real variables, and consider the following equation: a1 x1 plus a2 x2 plus dot 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 an xn is b. This equation is called a linear equation in variables x1 to xn. A1 to an are called coefficients, x1 to xn are called unknowns or indeterminants. Indeterminants. B is called constant term. It's again a real number. It's called constant term. Now, any values of x1 to xn that satisfy this equation are called solution to this equation. So, any values of x1 dot dot xn that satisfy the above equation is called a solution. Let us consider an example. Consider following equation: 2x plus 3y plus 4z equal to 5. It can be easily seen that 1 1 0, that is x is 1, y is 1 and z is 0, satisfies the above equation. Moreover, minus 1 1 1 also satisfies the above equation. Minus 2 plus 3 plus 4 will be equal to 5. So this also satisfies the above equation. So as per the statement above, 1 1 0 and minus 1 1 are solutions to the above equation. So we see that an equation can have more than one solution. Now let us extend these observations to more than one equations. So now we will fix numbers aij, where I is ranging from 1 to n and j is ranging from 1 to m. Also fix b1 dot 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 bm and consider variables as before, n variables x1 to xn. With these numbers and variables, let us write the following equations. a11x1 plus a12x2 dot 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 plus a1nxn equals to b1, a21x1 plus a22x2 plus dot 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 a2nxn equals to b2, and so on. We have m equations like this, the last one being am1x1 plus am2x2 plus dot 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 amnxn equals to bn. Now we, rather than one equation, we have m equations. This system is called, this set is called system of linear equations. This set of equations is called, also called, a system of linear equations. Let us now define a matrix A and vectors x and b as follows. Define A to be the following matrix: A11, A12, A1n, A21, A22, A2n, dot dot dot, AM1, AM2, AMN, and vectors B to be B1 dot 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 Bm, and X to be X1 dot 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 Xn. Then the above system of equations can be compactly represented as the matrix equation Ax equal to B. The above system of equations can be compactly represented as matrix equation Ax equal to B. Right? Following the terminology for single linear equation, here A is called matrix of coefficients, B is called vector of constant terms, and X is called vector of unknowns or indeterminates. Indeterminates. While analyzing the above system of linear equations in the following, we will come across another matrix which is obtained as follows. Here we write A, which is A11 to A1n, A21 to A2n, am1 dot 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 amn, and we attach to it the vector of constant terms. So we have b1, b2 to bn. This is clearly a m cross n plus 1 matrix. It's compactly represented as follows. And it's referred to as augmented matrix. In case of a system of linear equations, the system can have no solution, one solution, or infinitely many solutions. Let me elaborate. The system of equations Ax equal to b will always have a solution if b equals 0. In that case, the system of equations is called a homogeneous system of equations. It always has a solution. In particular, x equal to all 0 vector itself is a solution. If b is not equal to 0, then the system of equations is called non-homogeneous set of equations. In this case, there will be no solution if rank of A is less than rank of augmented matrix AB. There will be unique solution, that is one solution, if rank of A equals rank of AB, which in turn equals n, and there will be infinitely many solutions if a rank of A equals rank of AB but is less than n. Okay, let's see examples. First example is the set of equations x1 plus x2 plus x3 equals to 3, x1 plus 2x2 plus 3x3 equals to 6, and x2 plus 2x3 is 1. In this case, the coefficient matrix A equals 1, 1, 1, 1, 2, 3, 0, 1, 2. The vector of constant terms B equals 3, 6, 1, and the vector of unknowns x is x1, x2, x3. The augmented matrix AB equals 1, 1, 1, 3, 1, 2, 3, 6, 0, 1, 2, 1. Notice that in A, all three rows are not linearly independent. In fact, if I add the first and third rows, I get the second row. So rank of A is 2. On the other hand, it can be checked that rank of AB is 3. So rank of A is strictly less than rank of AB, and so the system has no solution. Let us see another example. Now we have system of equations Ax equal to b, where A equals the matrix 1, 1, 1, 1, 2, 3, 1, 1, 2, and B equals 3, 6, 4. In this case, it can be checked that a rank of A and rank of AB both are equal to 3. So the system has unique solution. Finally, let us consider Ax equal to b, where A is same as in the first example, that is A is 1 1 1 1 2 3 0 1 2, but B now is 3 6 3. Rank of A, as we saw, is 2, and now it can be seen that rank of AB is also 2. So A and the augmented matrix have same rank, but both is less than the number of variables 3. So in this case we will have infinitely many solutions. Now the question is, given a system of linear equations, we want to see if the system will have no solution, unique solution, or infinitely many solutions, and if it has a solution we want to find a solution. We will first see an algorithm that works in the case of unique solution, that is, it gives the unique solution if the system of linear equations has unique solution, and this method is called Cramer's rule. Let us see what Cramer's rule is. Cramer's rule says that for a system of equations Ax equal to b, it's if it has a unique solution, the solution can be obtained as follows. Says that the ith unknown xi can be obtained by dividing determinant of ai by determinant of a, where ai is the matrix that is obtained by replacing the ith column of A with B. Matrix obtained by replacing ith column in A with B. That is, AI is the following matrix. That's A11 dot 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 A1I minus 1, then I'll have B1, then dot 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 A1n, A21 dot 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 A1 A2I minus 1 B2 dot 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 A2n, finally am1 dot 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 am comma I minus 1 bm dot 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 amn. Okay, so the Cramer's involves computing n plus 1 determinants, computing n plus 1 determinants to obtain n unknowns, to solve for n unknowns. As I stated, Cramer's rule works only if the system of equations has a solution and has a unique solution. Next, we will see about a method that tells us whether a system of equations has no solution, has unique solution, or has infinitely many solutions, and in the latter cases it also provides us all the solutions to the equations. We will now see the notion of matrices in row echelon form, or simply row echelon matrices. However, I'll start with defining what is meant by pivot entries of a matrix. Pivots. So for a matrix, say M cross N matrix, the leading non-zero entry of any row is called pivot. The first non-zero entry of any row is called a pivot. For instance, if I consider A equal to say 1 1 1 0 0 3 0 2 3, then this 1 is the first non-zero entry in the first row, this is first non-zero entry in the second row, this is first non-zero entry in the third row. These are pivots. Okay. Next, a matrix is called in row echelon form in short REF, or it's simply called RE matrix, row echelon matrix, if the following two conditions are satisfied. First condition is all zero rows, that is rows with no pivots, are below non-zero rows. Rows with pivots. And the second condition is the pivot of a row is to the right of the pivot of the row above it. To the right of the pivot of the row above it. Let's see examples. Consider A equal to 1 0 2 0 0 0 1 0. Here we see that the 0 row, the second row is a 0 row, whereas third row is not. So first condition is violated. So A is not in row echelon form. Row echelon form. Or we can simply say that A is not a row echelon matrix. Okay. Similarly, if I consider A equals to say 0 1 0 1 0 2 0 0 0, again I see that 0 rows are below all non-zero rows, but the pivot entry of the second row is not on the right of the pivot entry of the row above it. So this A is also not in row echelon form. Okay. On the other hand, if you look at the matrix A, which is say 1 0 2 0 2 3 0 0 0, this is in row echelon form. Next we will see the notion of reduced row echelon matrices, which are special cases of row echelon matrices. Reduced row echelon form, in short RREF. A matrix A is called to be in RREF if it is in row echelon form and also satisfies the extra conditions that every pivot is 1 and it is the only non-zero entry in its column. In other words, the pivot columns are standard unit vectors. The columns of the pivots are called pivot columns. For instance, in this matrix A, all three columns are pivot columns. Let us consider again a few examples. Let A be matrix 1, 0, 1, 0, 2, 0, 0, 0, 0. This matrix is in row echelon form, but it is not in row echelon form because the pivot entry in the second row is not 1, not in reduced row echelon form. Okay, let's see another example. Now A is 1, 1, 2, 0, 1, 1, 0, 0, 0. Here we see that the pivot entries are all 1, but the second column, which is a pivot column, is not a standard unit vector. It's not in reduced row echelon form. Second column, which is a pivot column, is not a standard unit vector. Let's see one more example. Now A is 1, 0, 2, 0, 1, 3, 0, 0, 1. Again we see that the pivot entries are all 1, but this is also not in reduced row echelon form because the last column, which is a pivot column, has other non-zero entries also. Other than pivot, it has other non-zero entries also. It's not in RREF because third column is not a standard unit vector. Finally, let's see one more example where A is 1, 0, 2, 0, 1, 3, 0, 0, 0. Here we see that all the conditions are satisfied, namely the 0 row is below the two non-zero rows, the pivot entries are all ones, pivot entry in a row is on the right of the pivot entry in the row above, right? And all the pivot columns, there are two pivot columns here and both are standard unit vectors. That is, in both these columns, other than pivots, all other entries are 0. So A is RRE matrix, or A is in reduced row echelon form. Now we introduce elementary row operations. Elementary row operations. Elementary row operations are functions that map m cross n matrices to different m cross n matrices. There are three elementary row operations which are as follows. The first one is multiplying the ith row by a non-zero scalar lambda. This operation is denoted as Ri to lambda Ri. The second elementary row operation is interchanging ith row and jth row. Interchanging ith and jth rows. This one is denoted as this. And the third elementary row operation is for I not equal to j, replacing ith row by its sum with mu times the jth row. This one is denoted as Ri to Ri plus mu Rj. Let me illustrate these operations via simple examples. So let us consider A to be 2 by 2 matrix A, B, C, D. In this case, the elementary row operation R1 to lambda R1 produces matrix lambda A, lambda B, C, D. Similarly, the interchange operation produces C, D, A, B, and the operation R1 to R1 plus mu R2 produces A plus mu C, B plus mu D, C, comma D. Any finite composition of elementary row operations is called a row operation. A row operation refers to a finite composition of elementary row operations. Okay. Row operations. For example, an operation that produces, that maps a matrix to CD, A plus mu C, B plus mu D is a row operation because this conversion is obtained by iteratively applying two elementary row operations, namely R1 to R1 plus mu R2 and then exchange of R1 and R2. This is an example of a row operation. Okay. We will see that any matrix can be mapped to a reduced row echelon matrix using a row operation. Let us see how these elementary row operations affect determinants of the matrices. Right? So let row be an elementary row operation. So row could be one of these three operations. If row is ai going to lambda ai, then determinant of row a will be lambda times determinant of a. If row is interchange of two rows, then determinant of row a is negative of determinant of a. On the other hand, if row is ai going to ai plus mu aj, then determinant of row a is same as determinant of a. So from these we can infer that determinant of row A is non-zero if and only if determinant of A is non-zero. We further see that if row is an elementary row operation and A is an M cross N matrix, then row of A can be obtained by first applying row to M cross M identity matrix and then multiplying the resulting matrix with A. So in this way we see that if we know the effect of row on the identity matrix, then we also know its effect on a matrix A. Next we will see the notion of row equivalent matrices. Row equivalent matrices. So A, B are matrices of same order are said to be row equivalent if there is a row operation that is composition of finitely many elementary row operations many elementary row operations that maps A to B. Let's see an example. Let us consider A to be equal to 0, 0, 4, 3, 0, 0, 4, 2 and B equals to 0, 0, 4, 0, 4, 2, 0, 3, 0. Then clearly A and B are row equivalent as B is obtained from A by interchanging second and third rows. A and B are row equivalent. Similarly, if I consider C to be equal to 0, 0, 4, 0, 7, 2, 0, 3, 0. Notice that C is obtained from B via doing R2 to R2 plus R3. Okay, so C has also been obtained from A via a composition of elementary row operations. So A and C are also row equivalent. Next we see a very important result which will prove to be quite useful in the remaining of the lecture, that says that, and I will state it as a theorem, every matrix is row equivalent to a unique row reduced echelon matrix. Every matrix is row equivalent to a unique row reduced echelon matrix. In fact, given a matrix A, we can apply a sequence of elementary row operations to map it or to convert it to its unique equivalent reduced row echelon matrix. Unique equivalent reduced row echelon matrix. This successive application of elementary row operations is what is referred to as Gaussian elimination. Successive application of elementary row operations is called Gaussian elimination. We now illustrate Gaussian elimination via an example. Consider a 4 by 4 matrix A, which is as follows: 0 0 4 1 0 3 0 1 0 0 0 0 0 4 2 0. Now we will do a sequence of elementary row operations to convert it to a reduced row echelon matrix. Apply interchange of R3 and R4, and we will get 0 0 4 1 0 3 0 1 0 4 2 0 0 0 0 0. Next, apply interchange of R1 and R2, and this way we will get 0 3 0 1 0 0 4 1 0 4 2 0 0 0 0 0. We see that the pivot element in the first row is 3, so we apply R1 to 1 by 3 R1 to get 0 1 0 1 by 3 0 0 4 1 0 4 2 0 0 0 0 0. Next, we see that the second column, which is a pivot column, it's not a standard unit vector. To fix this, we apply R3 to R3 minus 4 R1, and we get 0 1 0 1 by 3 0 0 4 1 0 0 2 minus 4 by 3 0 0 0 0. Now we will focus on second row, and we see that the pivot element here is 4, so we apply R2 to R2 by 4 to get 0 1 0 1 by 3 0 0 1 1 by 4 0 0 2 minus 4 by 3 0 0 0 0. Now we see that again the third column, which is a pivot column, is not a standard unit vector. To fix this, we apply R3 minus to R2 to get 0, 1, 0, 1 by 3, 0, 0, 1, 1 by 4, 0, minus 0, 0, minus 11 by 6, 0, 0, 0, 0. Now we will look at the third row and notice that the pivot entry is not 1. To fix that, we apply R3 to minus 6 by 11 R3, and this way we get 0, 0, 0, 1 by 3, 0, 0, 1, 1 by 4, 0, 0, 0, 1, 0, 0, 0, 0. Finally, we see that the fourth column, which is also now a pivot column, is not a standard unit vector. To fix this, we apply R1 to R1 minus 1 by 3 R3 and R2 to R2 minus 1 by 4 R3 to get 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, and this is a reduced row echelon matrix. So we saw how we could apply a sequence of elementary row operations to convert A to its equivalent reduced row echelon matrix. We will now see several uses of Gaussian elimination or uses of reduction to RRE form. The first application is computation of determinants. Computation of determinants. We have already seen how elementary row operations affect the determinant of matrices. We can now adopt the following procedure to compute determinant of any matrix. Given a matrix A, say of order n cross n, we can reduce A to reduced row echelon form. In fact, we can stop the Gaussian elimination procedure as soon as we get an upper triangular matrix. Stop Gaussian elimination once an upper triangular matrix is obtained. So we need not go all the way to reduced row echelon matrix. Now we can easily write the determinant of the upper triangular matrix so obtained. So suppose Gaussian elimination stops at B. Elimination stops at matrix B, then we know the determinant of B is just the product of I equals to 1 to n. Now we also know how the determinant of A is related to determinant of B. We also know the relation between determinant of A and determinant of B. we can use this relation to recover determinant of A from determinant of B. Can use this relation to obtain determinant of A. Let us see an example. Consider matrix A equal to 1, 1, 1, 1, 2, 1, 1, 2, 3. Let us start Gaussian elimination in an attempt to convert A to a row reduced echelon matrix. Okay, so we will first do R2 to R2 minus R1 to get 1, 1, 1, 0, 1, 0, 1, 2, 3, and we know that determinant of this new matrix is same as determinant of A. Next we will do R3 to R3 minus R1 to obtain 1, 1, 1, 0, 1, 0, 0, 1, 2, and the determinant of this new matrix also remains unchanged, so it's same as determinant of A. Then we will do R1 to R1 minus R2, and this way we will get 1, 0, 1, 0, 1, 0, 0, 1, 2. Again, this operation doesn't alter the determinant, so determinant remains same as determinant of A. Next we do R3 to R3 minus R2 to get 1, 0, 1, 0, 1, 0, 0, 0, 2. This operation also doesn't alter the determinant, so determinant remains same as determinant of A. And now we have an upper triangular matrix, so we can stop the Gaussian elimination process and can also readily compute the determinant of this terminal matrix as 1 into 1 into 2, which is 2. So this way we see that determinant of A is 2. The next application is checking whether a set of vectors is linearly independent. Checking whether a set of vectors is linearly independent. Okay, so suppose we are given n vectors v1 to vn, each of them is a vector of length m, v1 to vn in Rm, and we have to determine these vectors are linearly independent or not. What we do is we write a matrix A with v1 to vn as columns of A. v1, v2 dot 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 vn. So this A is a m cross n matrix. Now we reduced A to reduced row echelon form. It turns out that v1 to vn are linearly independent if and only if all the columns in the reduced row echelon form of A are pivot columns. All the columns in RREF of A are pivot columns. Let us consider an example. Suppose we are given three vectors 0, 3, 0, 4, 0, 4, 0, 0, 2 and 1, 1, 0, 0. We will form a matrix A with these three vectors as columns. So A is 0, 3, 0, 4, 4, 0, 0, 2, 1, 1, 0, 0. Observe that this A is same as the second, third and fourth columns of matrix A that we took an example a while ago. So a reduced row echelon form of A as we saw then would be 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. We clearly see that all the three columns of A are pivot columns. Dependent. All the three columns are pivot columns. So the three vectors are linearly independent. So the three given vectors are linearly independent. The third application that we will consider, determining the rank of a matrix. It turns out that if two matrices are row equivalent, then their ranks are same. Row equivalent matrices have same rank. Also, the ranks of reduced row echelon matrices are same as number of non-zero rows. Are same as number of non-zero rows. Finally, if we are given M cross N matrix, given A, that is an M cross N matrix, rank of A is same as a rank of reduced row echelon form of A. This tells that we can use Gaussian elimination to reduce A to reduced row echelon form and thereby to get the rank of A. Let us consider an example. Suppose A is a 4 by 5 matrix which is as follows: 1, 1, 1, 1, 1, 1, 2, 1, 3, 1, 0, 1, 0, 2, 0, 1, 0, 1, minus 1, 1. It can be seen that the reduced row echelon form of A happens to be 1, 0, 1, minus 1, 1, 0, 1, 0, 2, 0, 0, 0, 0, 0, 0. And the last row is also all 0 vector. So we see that reduced row echelon form of A has two non-zero rows. So its rank is 2. So rank of A is also 2. The next application that we see is computing the inverse of a matrix. We have already seen that determinant of a matrix is Non-zero if and only if determinant of its row reduced row echelon form is non-zero. This tells that A is invertible if and only if reduced row echelon form of A is invertible. A is invertible if and only if reduced row echelon form of A is invertible. A reduced row echelon matrix is invertible if and only if it is an identity matrix. Moreover, we can adopt the following procedure to determine if a matrix A, say M cross N matrix, is invertible or not, and if it is invertible, what is its inverse. So given A, which is M cross N, here is the procedure. We first write an augmented matrix which is A IM. Okay, IM is M cross M identity matrix. Okay, then we convert AIM to reduced row echelon form. Suppose RB is a reduced row echelon matrix and is row equivalent to AIM. That is, suppose the Gaussian elimination of AIM terminates at RB, then A is invertible if and only if R is identity matrix, that is R is IM. Moreover, inverse of A is B. Let us understand it via an example. Let's again consider A to be equal to 1, 1, 1, 1, 2, 1, 1, 2, 3. We will first write the augmented matrix AI3, which clearly is 1, 1, 1, 1, 0, 0, 1, 2, 1, 0, 1, 0, 1, 2, 3, 0, 0, 1. If we apply a sequence of elementary row operations, it can be seen that AI3 is row equivalent to matrix RB, that is 1, 0, 0, 0, 1, 0, 0, 0, 1, 2 minus half, minus half, minus 1, 1, 0, 0, minus half, minus half. Clearly, R here is an identity matrix. So, A is invertible, and moreover this submatrix B is inverse of A. So, A inverse is 2 minus half, minus half, minus 1, 1, 0, 0 minus half, minus half. We now discuss another application of Gaussian elimination, namely solving systems of equations. Solving systems of linear equations. Consider a system of linear equations Ax equal to b, We start with a very important result that we state as a theorem. It says that if AB is row equivalent to A prime B prime, then the two systems that is Ax equal to B and A prime x equal to B prime have identical solutions, the same solutions. Recall that the number of solutions of A prime x equals to B prime is governed by the rank of A prime and A prime B prime. In particular, it has no solution if rank of A prime is less than rank of A prime B prime. Unique solution if rank of A prime is equal to rank of A prime B prime equals n, and it has infinitely many solutions a rank of A prime equals a rank of A prime B prime, but it's less than n. Now suppose A prime B prime is in row reduced echelon form. Suppose A prime B prime is a row reduced echelon matrix, then we can obtain a rank of A prime and a rank of A prime B prime, and also the solutions to A prime x equals to B prime merely by observation. In particular, if a rank of A prime equals to rank of A prime B prime is R, which is less than n, then we have R pivot columns and n minus R non-pivot columns. In this case, the unknowns corresponding to non-pivot columns can be set arbitrarily and are called independent unknowns, and the unknowns corresponding to the pivot columns can be expressed in terms of independent unknowns and are called dependent unknowns. We will illustrate these notions through a few examples. In fact, We will revisit the examples seen at the beginning of the lecture. So let us start with first example. Here we take A to be 1 1 1 1 2 3 0 1 2 and B 3 6 1. In this case, augmented matrix AB is 1 1 1 3 1 2 3 6 0 1 2 1. If we apply elementary row operations, A and AB are reduced to reduced row echelon matrices. A and B are reduced to 1 0 minus 1 0 1 2 0 0 0 and 1 0 minus 1 0 0 1 2 3 and 0 0 0 minus 2 respectively. Let us call these matrices A prime and A prime B prime respectively. Then since A prime has two non-zero rows, can be directly seen that rank of A prime is 2, and following a similar argument, rank of A prime B prime is 3. So A prime x equals to B prime has no solution, and so Ax equal to B also does not have any solution. Let's look at another example. Now A is 1 1 1 1 2 3 1 1 2 and B is 3 6 4. The augmented matrix now is AB equals to 1 1 1 3 1 2 3 6 1 1 2 4. Again, if we apply a series of elementary row operations, A and AB reduced to reduced row echelon matrices. One 0 0 0 1 0 0 0 1 and 1 0 0 1 0 1 0 1 0 0 0 1 respectively. If I define the first one to be A prime and second one to be A prime B prime, now I see that a rank of A prime is same as rank of A prime B prime. Both have same number of non-zero rows, that is 3, and so Ax equal to B has a solution, has a unique solution, and this unique solution can be directly read from A prime x equal to B prime, which is nothing but x1 equals to x2 equals to x3 equals to 1 in this case. Let us now see one more example. Now A is 1 1 1 1 2 3 0 1 0 1 2 and B is 3 6 3. The augmented matrix now is 1 1 1 3 1 2 3 6 0 1 2 3. Now if we apply a series of elementary row transformation, we get a reduced row echelon augmented matrix, that is RRE augmented matrix. 1 0 minus 1 0 0 1 2 3 0 0 0 0. As before, if I use A prime to denote this submatrix and A prime B prime to denote the whole matrix, then I see that rank of A prime is 2 and rank of A prime B is also 2. These can be seen merely by observing the matrices A prime and A prime B prime. Moreover, notice that the first and second columns of this matrix are pivot columns. Hence, x3 is an independent unknown and it can be set arbitrarily. Let x3 be lambda. On the other hand, x1 and x2 are dependent unknowns The values of x1 and x2 depend on x3 as follows. x1 minus lambda is 0 and x2 plus 2 lambda is 3. These two equations together give x1 equals to lambda and x2 equals to 3 minus 2 lambda. Clearly, in this case we have infinitely many solutions. A general solution will be of the form lambda 3 minus 2 lambda comma lambda. Setting different values of lambda, we obtain different solutions. This brings us to the end of this lecture. Thank you.